I will wait another minute or two before getting started to give people a little longer to connect. Okay, maybe we'll go ahead and get started with the lecture for today. So thanks everyone for attending. This is the final lecture that we have planned for this academic year, for the 2021 academic year, for this Saturday physics series. And so we're really glad that you could take some time out on a Saturday here to join us. I'm Alicia Marino, one of the organizers for this talk series. And I also really want to thank Veronica Lingo, who has been helping with all of the setup of the video conferencing for this year in this virtual format. And I hope that we'll be able to return to in-person lectures next fall, so keep an eye out for that. Yeah, but today, there's a comment that there's bad echo, I'm not sure. All right, so I'll say that this talk is being broadcast on Zoom, but it's also being live streamed simultaneously on YouTube. And so if at some point you run into connection or internet difficulties, you might want to try to connect to watch it live on YouTube as well. Today, for our final talk for the year, we're really excited to have Dr. Ana Maria Rey. And Dr. Rey got her bachelor's degree in physics from the Universidad de los Andes in Bogota, Colombia. She got her PhD in physics from the University of Maryland, and then did postdoctoral work at NIST and also at Harvard. And then in 2008, she moved to Boulder, where she has a joint position at the Joint Institute for Laboratory Astrophysics at JILA, and also has an adjunct faculty position in the physics department at the University of Colorado. She's won many awards. I really can't list them all. She's an extremely distinguished researcher. For example, she won an award for outstanding doctoral dissertation in atomic, molecular, and optical physics from the American Physical Society. She's won a number of early career awards for scientists, including the Blavatnik National Award for Young Scientists, and also a Presidential Early Career Award from the US government. She's also won a MacArthur Fellowship from the MacArthur Foundation. These are sometimes referred to, maybe you've heard as Genius Grants, and many other awards, and she's also a Fellow of the American Physical Society, so very distinguished research career. And her research is at the interface of atomic, molecular, and optical physics, and also quantum information science. And she's especially interested in new techniques to control quantum systems, and then to apply these techniques to systems such as atomic clocks, which is what we're going to hear about today. So yeah, we'll go ahead and welcome Dr. Rey. And throughout the talk, if you have really urgent questions, you can try to type them in the chat or the Q&A, and we'll try to keep an eye on those. And then also, we're very happy to have you stick around and ask questions after the talk as well. Again, you can try typing in the chat or in the Q&A. If not, let's go ahead and welcome Professor Rey.
Oh, thank you, Alicia. Well, let me start by thanking Alicia, Veronica, and the organizers of the faculty of the Saturday Physics series for the opportunity to talk today. And of course, let me thank you for being present. Unfortunately, this talk is via Zoom, but it would have been ideal if it were in person. But well, given the circumstances, hope any way that we can all of us learn and enjoy this presentation that is about atomic clocks. So I want to start by asking you to look at this picture and think about what you see there. I would give you a minute to carefully look at it. Okay, well, in fact, this is an artistic representation of an atomic clock. It's made with atoms and light. So the atoms are these things that you hear here with these green dots, and the light are these red beams. So what you are going to learn today is the fascinating idea of how atoms and light can be used to create atomic clocks, the most precise timekeeper ever imagined. But wait, did you see something also weird about this picture? Well, yes. Seems that this is kind of an spy. Why? Well, because what I'm going to tell you too is that atomic clocks can be serving as a spies of the quantum world, and they are helping us to unravel the weird mysteries associated with it, and in fact, are going to allow us to answer questions that we even don't understand now. So in this talk, we are going to take a look at the inner workings of atomic clock. And even if I don't convince you to become a clockmaker yourself, I hope that at the least I can convince you that atomic clocks are not only fascinating and exciting, but very important for us. All right. Let's see. Now it's my. Okay. So a clock is a measurement device. It ticks in a repeated manner to measure time. And any clock is made of two basic parts: an oscillator, that is what ticks, and the counter, that is what measures each tick. So let's stop and think about the measurement of time itself. For example, we make appointments, we worry about all those terrible deadlines, but perhaps the question is why we care to measure the time so precisely. Well, it happens that measurement of time has been essential for mankind since its early existence. For example, in the beginning, the Earth orbit around the Sun was the most natural, regular, accessible oscillator. Early Egyptian civilization measured the time with the development of the famous sundials. So this was followed, for example, by the development of the mechanical pendulum. And then, for example, it came the electromechanical quartz crystal clock that we are all familiar with. And well, perhaps we are now changing for our iPod clocks. But well, important point is that each man-made clock was an incredible step forward in the measurement of time. But the problem is that each clock is vulnerable to error because it's man-made. Um, so, for example, a high-quality electromechanical quartz clock may still lose on average a second in a year. So today, the most precise clocks in the world are atomic clocks. They can make the most accurate measurements of time. And this has been the focus of my research. And what we have been working on is try to make the clocks even better. Okay, so I want to say, nevertheless, that I'm not the actual clockmaker. I am not an experimentalist. I am a theorist, and I do not make the clock, but I model the clock. The actual clockmaker is shown here in the plot is John G. But in my field, as in many other fields in science, is the synergy between theory and experiment that have allowed us to make a lot of progress and actually accomplish major advances. So the questions that you might be asking yourself is, why would anyone want to improve on the most accurate clocks in the world? And I can answer these questions in 2 words: quantum technologies. But before we can truly grasp the significance of quantum technologies, let's think a bit about the quantum world itself, the world of atoms, electrons, quarks, and more. And for that, let me start by reviewing what is an atom. So an atom is the smallest unit of an element having all the characteristics of that element. So matter is made of atoms, but nevertheless, we know atoms are not fundamental ingredients. Well, atoms themselves are made of electrons, neutrons, and protons. And well, neutrons and protons, for example, are not also the fundamental units. They are made of quarks, and you find gluons. But anyway, so for this talk, it would be enough to visualize the atom as a unifying part of matter. Because that's what we are going to deal with. We are not going to be able to explore, for example, the most internal pieces of the atoms. All right, so let's now take a step back and compare the classical world, that is the physical world we see and we move through every day. For example, these are the streets of Pearl Street, with the quantum world. And for that, let me compare the 2 worlds using 2 simple balls, as as you can see here. You can see a red ball and a blue ball. In the classical world, we can distinguish these 2 balls. Well, obvious, there is one red and there is one blue. We can place these balls in a box, and actually we can push these balls and start throwing throwing in the box. We see that these balls are going to bounce and move inside the box. And this is kind of the natural behavior. So these balls bouncing inside the box. But actually, things are different in the quantum world. For example, you can imagine that in this case, the balls are atoms or an electron. So in this case, yes, each ball can be either blue or red, but also there can be blue or red at the same time. Actually, in quantum mechanics, quantum superpositions are allowed. Moreover, now, if you throw these balls at the wall, you expect the balls bounce back and forth like in the quantum world, but this is not necessarily always the case. Actually, in the quantum world, they can go straight through the barrier walls of the box in a phenomenon that is called quantum tunneling. So this strange behavior of the quantum world, which is fascinating and useful, is described by quantum mechanics. And quantum mechanics, even if you cannot believe it, it has revolutionized our understanding not only of how atoms, electrons, and light behave, but actually it has allowed us to develop the technologies that we have now. For example, quantum mechanics has been fundamental for the development of transistor devices, these very tiny pieces of semiconductors that we use in modern computers, in cell phones, and everything that shapes our modern life. Actually, it happens that quantum mechanics is what tells us how these semiconductors behave, how the electrons in superconductors behave. And thanks to that, we have been able to build these transistors. But besides this, quantum mechanics has been also fundamental in the way that we communicate and transport, even if you cannot realize that or have not realized it. In fact, for example, as you navigate in crowded cities, you do it by using GPS technology that is right at your fingers, either in your cell phone or in your car. But what you might not realize is that at the heart of your GPS is the 24 GPS satellites that are actually perform this GPS system. And in fact, each of these satellites must contain at least 4 atomic clocks, and atomic clocks are ruled by the laws of quantum mechanics. So quantum mechanics has been also fundamental in GPS, which we use to synchronize communications, for navigations, and even for financial transactions. So atomic clocks are really quite important in our everyday lives. All right, so let me try to explain you now how an atomic clock works. So as I mentioned, a clock has an oscillator and a counter. It's exactly the same for atomic clocks. In this case, the light is what it ticks, like light is the oscillator, and what counts the light are the atoms. So the question that you might be asking is how atoms count the light, how they are acting as a counter of our clock, and why atoms are so useful. And the answer for that is that atoms are ruled by the intrinsic laws of quantum mechanics, and this is what they make them so useful for measuring, for counting the oscillations of the light. So, for understanding that, you need to realize that actually, because of quantum mechanics, the energy levels of an atom cannot take continuous values, but on the other hand, the energy levels of an atom are discrete, so they only can take specific values. Imagine instead of a ramp, you have an stairs, so you can only advance step by step. In the case of the atoms, what happens, or how you can visualize and understand that they have discrete energy levels, is that by imagining that the electron that circulates around the nuclei can only do it in discrete orbits. So this is one orbit and this is the other orbit. And if you want to excite the atom, the electron here from one orbit to the next, actually, the only way to do it is to provide the exact amount of energy that requires go from here to here, or vice versa. They can only emit energy that has this amount. So, light is an electromagnetic wave, as we all know, but also all light is can be understood from quantum mechanics as quanta, little discrete packets that have a specific energy. So Einstein told us that there is actually a relationship between this energy of these light quanta that are called photons and the associated frequency of the electromagnetic wave that the light described by the light. So the proportionality between these two is a constant that is called the Planck constant, H here. You can see this H. I don't know, my mouse is not working that well, but hopefully you see the H. So this is the proportionality constant. But the important point here is that what happens is that in order for an atom go from here to here, it can only absorb light of a specific frequency. And remember, a frequency, because the light is an electromagnetic wave, means or corresponds to the number of oscillations per second. So there is a connection between frequency and time, and that's why atoms are so useful to actually set a standard of time. So in particular, atoms are a perfect measurements of frequencies because, well, only a specific frequency can excite my atom on one hand, but on the other, this frequency is universal. That means that the energy splitting between two levels of an atom is exactly the same here in Boulder or the same that someone in China will measure. So we have a universal standard, and therefore this helps us to provide an unrivaled definition of the second that lacks mankind error. It's universal, it's intrinsic, it comes from nature. So in fact, the energy splitting of two internal levels of cesium atoms are actually what set the definition of the second since 1967. So let me recall you that, remind you that atoms are, the elements can be displayed in the periodic table. And for example, cesium, atoms like here, that they are atoms with one outer electron. So in fact, the definition of the second, since this period of time, since 1967, has been the duration of 9,192,631,770 periods of radiation, the radiation of the cesium atom that can that can excite the transition between two specific energy levels of cesium. That's how we define the second, the number of oscillations associated with, of the frequency associated with this transition. Okay, even though the cesium is used for the standards now, actually the first atomic clock made of cesium atoms was built in 1955. This clock was made by Essen and Parry, and this clock lost a second every 100 years. So it was very good at that time. But the point is that through decades, we have been able to significantly improve the error of these clocks. So it is, actually 1 second in 100 years corresponds to an error of 10 to the minus 9. So you have 9 zeros of 0.000001. This is the first, the uncertainty of this first clock. And as time went on, we were able to actually improve the frequency or the uncertainty that we can measure a frequency with this clock for a few decades. But then there was a stop. We were not be able to progress anymore, and not only in the after the 1990s is where we were able to actually continue the progress and actually start to reach the uncertainties that we currently have with cesium fountain clocks. I'm going to tell you more details about this clock in a few seconds. The story that I want to tell you now is what made a big difference and what allowed us to actually improve this gap. And what allows us to improve this gap is the capability to laser cool and trap atoms. The point is that atoms in room temperature are moving extremely fast, and motion is bad for clocks because a phenomena that you might be all familiar with, that is the phenomena of the Doppler effect. If you hear a car, actually the frequency of the car approaching you is faster than the frequency of a car that recedes from you. It's the same phenomena for atoms. So atoms will feel a different frequency depending on the motion. And because we have many atoms and all moving at different rates, and therefore if they actually is going to experience different frequencies of the light, then it's going to be terrible because it's going to be a very bad clock. That's the problem, but we could not improve the clocks before. So in order to make progress, we need to slow down the atoms and reduce their velocity. So how we can do that? What is the trick to slow down the atoms? Well, actually there is a connection between the velocity of the atoms or their kinetic energy and actually the temperature. There is a one-to-one relation. And making the atoms slower means reducing their temperature. And actually, one of the big progress that we had in the last couple of years was the possibility to use lasers to cool the atoms. So at room temperature, like it's about 300 kelvins, the atoms are actually moving close to the speed of sound, around 300 meters per second. And if you think about the coldest temperatures that you can naturally get in the universe, perhaps the temperature of the outer universe, the temperature is not that far from 4 Kelvin. That is the temperature, for example, with helium condense. And at this temperature, still atoms are moving very, very fast, 90 meters per second. So it was the big accomplishments that led to the Nobel Prize in 1997 that we could use laser lights to reduce the velocity of the atoms and therefore the temperature to velocities of just few meters per second and below. This was done by three scientists, Steve Chu, Coin Tanuji, and Bill Phillips, using, as I said, lasers. That the idea is to bombard the atoms with light, and by doing that, we should be able to cool down and slow them down. The idea is very simple. So as I mentioned, only at specific frequencies of light the atoms can absorb the light. And when atoms, imagine that the light again is kind of a small quanta, a particle. If the light is or the photon is moving against the velocity of the atom, then when the atom absorbs this photon, it's going to experience a kick in the opposite direction at which the atom is moving. What happens, therefore, is that after that, the atoms they start to slow down. And therefore, if we illuminate the atoms with laser beams along all the possible directions, what is going to happen is that we are going to slow them down and cool them down. And that's the essence of laser trapping and cooling. So, as we were able to actually reduce the velocity of the atoms, then they were in conditions where Doppler shift was not very important and we could prepare better clocks. So here in this movie, I want to show you actually, this is a small movie, a short movie of how the Cesium clock operates. It's called fountain clock, as you will see in this animation. The basic idea is you have a device that is able to collect cesium atoms that are whole. So, well, the idea is that we have all the gas of cesium atoms. We then trap them and then start to cool them down with lasers in the processes that I mentioned before. We cool them down and then we use the same laser to launch them up and then illuminate them with microwaves with light. And depending on the frequency of the light that we use, we should be able to excite or not the atoms. So, for example, if you use the ground frequency, a frequency that is below the atomic transition, we are only going to excite a few atoms. But when we actually excite them at the proper frequency, when actually the atoms can really absorb the light, then we are going to have the maximum response. We are going to excite the majority of the atoms. If we, for example, tune our laser and our microwave frequency a little bit even up, now faster, the waves are faster than the atomic transition, then and again, the light is not on resonant with the atoms, and as a consequence, I'm going to have less atom excited. So by doing this process, I are able to actually lock my microwaves with the frequency of the atomic transition. Then I know that what is the actual frequency of my transition, that is the frequency of the cesium atoms, and this allows us to provide a definition of the second that is now used as the standard in the SIE, International Systems of Units. Okay, so now that we learn about cesium, what I'm going to also tell you is that actually the cesium clock is currently not the best in the world. We are doing better clocks. We are making better clocks. And for seeing that, actually, I'm showing you these two rulers, ruler A and ruler B. And I'm going to ask you, what ruler is more precise? What ruler is using to measure a better measurement device? Well, I hope you are all of you saying, well, definitely the one that have more ticks gives me higher resolution and it's better. Actually, it's exactly the same for clocks. The cesium clocks operate with a transition frequency that is exacted with microwaves that has a frequency of the order of gigahertz. On the other hand, if we use atomic clocks that operate with an optical transition, the light that we need to excite this transition has to oscillate much more faster. It has to oscillate approximately 10,000 times faster than the microwaves. So these clocks have more ticks and therefore allow me to have better resolution, better clocks. So in this clock now, the light, because it's faster, is not microwaves but a laser, and we have to use the appropriate atoms that can actually absorb and be useful for this type of frequencies. Actually, the type of atoms that we use are not the atoms in the first column of the periodic table, but strontium atoms. These are the ones that we are using to operate the best atomic clocks, these optical clocks. And why? Because due to this atomic structure that has two outer electrons instead of one, like cesium, actually we are able to have transitions where when I excite the atom in the excited state, it lives for very long times. So I can illuminate this transition for very long time without losing the signal, allow me to measure the frequency very precisely. So actually, what happens is that if we imagine the atom, this two-level system as equivalent of a pendulum, with a quality factor determined by the frequency of the pendulum divided by the damping rate, we will get that this atom corresponds to a pendulum with a quality factor larger than 10 to the 17. So it would be a pendulum when it's set to swing. It would swing for the entire age of the universe. So they're very good atoms that allow us to measure for a very long time these fast optical transitions. Okay, but besides the atoms, we need to trap them and prevent them to move. So before in the cesium clock, I would tell you they were launched and we didn't need to trap them very tightly. Actually, for this type of clocks, actually the trick is to trap the atoms very tightly to prevent them to move. And how we do that? We also trap the atoms with light, forming what we call an optical lattice, that is an artificial crystal of light. Basically, what we do is we get two interfering laser beams that propagate in space but in opposite direction, and they form what is called a standing wave that have exactly this shape. So atoms, actually in the presence of this light, when they're illuminated by this light, first a force that is proportional to the intensity of the light. So therefore, when we illuminate the atoms with this pattern of light, they are going to be trapped at the bottom of the wells, and we are going to prevent them to move. That's great for clocks, because what I can do is that I can illuminate them with my laser such that perpendicular to my laser they cannot move because of this tight confinement, and the only way that they can move is in these pancakes, but it doesn't matter because they doesn't generate any Doppler shifts. So that's great. But nevertheless, even though there are no Doppler shifts, there was a dilemma. The idea is that, of course, if we have more atoms, we are going to have a better signal to noise. But what it was realized is that in these pancakes, if I have many atoms, these many atoms start to collide, and when they collide, they change their frequency. So packing more atoms make an error, and the more atoms we have, even though we have more signal to noise, the error is worse. So that's very bad. Collisions are evil, very bad for us. So the idea was to use the properties of the quantum world to kind of prevent these nasty guys, these nasty collisions. So for that, let me tell you another secret of quantum mechanics is that particles have a spin. If spin is an intrinsic angular momentum, you can understand, for example, that electrons, protons, neutrons have a spin 1/2, and you can associate with two different types of circulations. If that means they can circulate in two ways, or the right or clockwise and anti-clockwise. So this corresponds to a spin up when it's clockwise and anti-clockwise to a spin down. So, but then because atoms are made by electrons, protons, and neutrons, then the total spin on an atom depend on the number of electrons, protons, and neutrons that form the atoms. And depending on the total spin, my atoms can behave differently quantum mechanically. So actually, there are two types of particles in nature. What we call bosons, named in honor of Charles Eckhart Bose, that these bosons are the particles that have integer spin. And interestingly, these bosons are boring. They want all to do the same thing. They want to replicate what their neighbor does. On the contrary, example of them are the helium-4 that has 2 protons, 2 neutrons, and 2 electrons. On the other hand, fermions, named in honor of Enrique Fermi, have integer spin, like 1/2, 3/2, and so forth. And they don't, no two fermions can occupy the same quantum state. It's forbidden by quantum mechanics. And they're forced to be different, completely different, independent guys. These are my fermions. An example, as I said, are protons, neutrons, electrons. So actually, June, the clockmaker, had the idea to use fermions to prevent the collisions in the clock. Why? Because actually collisions again happens in quantum mechanics in a quantized manner and are characterized by an angular momentum L. It's a number that is an integer. And a statistic matter for these collisions. So if I have fermions, because they cannot be in the same internal state, two fermions cannot collide via S-wave, the lower energy collisions. And the only way that my fermions can collide is to gain energy and go to the L equal to 1 channel. This requires energy, but if we are at low temperature, this energy does not exist, and we can't suppress these collisions. That's great. So that was June's idea. Let's try to suppress the collisions by using fermions, by taking properties of the quantum world into account. But the bad news is that his clock was so precise that even if the collisions when fermions were slightly suppressed, they still give rise to the largest uncertainty in his error budget back in 2008. That was the time when I was coming to JILA. And during these years, what we have done, and unfortunately I don't have time to explain you details, but we have tried to understand these complicated collisions in the clock. And we have been able to control them and manipulate them. And nowadays, by understanding of the many body physics associated with these collisions, what happens is that they are no longer a problem. And by controlling these collisions, June and I were able to actually build and improve a clock that never so precise that these new clocks never gain or lose 1 second in about 15 billion years. This means roughly the edge of the universe. That's so precise, these clocks, very precise. And why this is useful? Because with this precision, they're allowing us to explore these weird aspects of the quantum world. So, for example, let me try to give you this cartoon that tries to convey this message. Imagine you are the Cesium clock, not very good. You can only operate for short time. And I will ask you, what do you see? Again, what do you see? Maybe you just say, I don't know, I don't see anything, nothing clear. Now imagine that you are the JILA Strontium clock, and I will ask you, what do you see? Okay, hopefully all of us saw a hydrogen atom. So that's the idea. We are able to use this clock to resolve the quantum world and spy on it and extract the information. And why is that so important? Because unfortunately, the quantum world is really complicated. I told you with the example of the 2 balls that superpositions are allowed. But actually, I was showing you only 2 states, red and blue. But in nature, for example, even if you consider just a small system of 6 atoms and 3 sides, and you're trying to count how many possible states that you can configure this system, like 6 atoms, all the atoms in one box, 0, 0, all atoms in the other box, and 0, 0, actually there are 84 configurations. But if you multiply this number by 10 and this number by 10, and you count the number of configurations, it's larger than the Avogadro number. It's huge. So in order to solve a quantum problem where quantum superposition holds, even our best supercomputers are going to fail because they cannot store all this information in their memory. So a classical computer cannot tell us information about the intrinsic character of the quantum world. So, but there was a salvation, and that was pointed out by Nobel Prize winner Richard Feynman. What he said Well, maybe we can build machines that operate with quantum mechanical elements by themselves, and then actually we can use these machines to create a quantum computer, and because it's operating with quantum mechanical elements, it can actually simulate all possible quantum mechanical problems that ever we want as the machine to solve. This is the idea of a quantum computer. He realized that was also very challenging, and he said, maybe we can create not a digital, a very universal quantum machine, a little bit something less universal, but we just use a full controllable quantum system that we can poke, manipulate, modify to emulate the behavior of other quantum systems that we need to understand, but we cannot. And this is the idea. We are now using atomic clocks as quantum simulators of the behavior of electrons in solids, because atoms in clocks live in this periodic lattice potential, this crystal of light that emulates the periodic structure that electrons feel in solid state crystals. However, these are fully controllable, these are not. And what we have been able actually to do is actually use and control the behavior of the atoms in the clock to emulate some aspects of the electrons in solids that actually we don't understand. And at the moment, it has been just baby steps, but we step in the future, we should be actually able to understand much better the world around us. So, for example, I'm going to tell you a few examples of what we have accomplished. Atoms are neutral, electrons are charged. Nevertheless, by illuminating atoms with light, we have been able to make atoms behave as electrons in very, very strong magnetic fields. It's magnetic fields of more than 1000 Tesla that are very hard to achieve in real life. Moreover, by studying atoms in the clock, we have been able to emulate the first principles of models that actually theorists used to actually believe that rule the behavior of quantum magnets and superconductors. So we are starting to use the clock to actually probe the physics of these systems and explore them with all the control that we have. And moreover, and even more interesting, actually, even though I have two outer electrons, the atoms also have what is called the nuclear spin because it have a nucleus. And in the case of strontium atoms, that the atoms that we use, this nucleus can have 10 different flavors, and that has some symmetry that is very similar to the symmetry that quarks show up inside the protons. So actually, we have been able to use the atoms to emulate the behavior, the symmetries that quarks experience, that quarks features. And actually, we have not only in quarks, there are only three symmetries. In the atoms, we can control the symmetries from 1 to 10, including 3. So there are many aspects of the quantum world that should be able to start explore with these clocks. Well, but this is just the beginning, so I don't want to overwhelm you with details, but what I want to finish this talk in the next couple of slides is to tell you that there are great vista ahead. There is a great vista ahead. In particular, we are now, and we theorists, we are collaborating with the group of June, trying to actually use these atoms in the clocks, actually to emulate some first preliminary steps that you need for creating a quantum computer. Basically, we are trying to use the internal states of the atoms in the clock as quantum bits, and with that we are using the clock, the laser in the clock, to control these atoms and try to generate gates that in quantum mechanics is called quantum gates, and we are trying to use these gates to actually form the first stage of a quantum computer. Everything, of course, is just work in progress, but June's lab is starting to actually make the first preliminary steps towards this direction. And finally, the clock actually is very sensitive to shifts that the atoms can experience because of gravity. Actually, depending of the height of the atoms, they're going to tick at a different rate, because Einstein taught us from general relativity that actually there is something that is called redshift, that depending of the altitude of your particle, your time is going to be different. So atomic clocks are starting to reach the precision where actually they are starting to feel, to observe, to experience the difference between two positions, two heights, two different atoms at different heights, and therefore we should be able to start to connect these quantum objects that are ruled, atoms in the clock are ruled with quantum mechanics, with general relativity, and perhaps shed light into the phenomenon of quantum gravity. And hopefully there are a lot of questions on this part of the physics, and we hope that actually atomic clocks can bring the necessary tools for us to unravel these mysteries of quantum gravity. And of course, we want to combine everything on the same system. So not only we want to use these clocks as quantum simulation, we want to use a quantum computer. We want to generate use these atoms and synthetic materials, because we can really modify the the properties of the lattice that we use to trap the atoms, and hopefully unifying them, we should be able to use atomic clocks for build the next generation of quantum technologies. So with that, I'm going to finish because I want to give time of you to ask questions. So just let me thank you for your attention.
All right, thank you very much for this fantastic talk. Yeah, if people have questions, feel free, if you're on Zoom, to type them in the chat, or there's a Q&A button at the bottom of your screen. And I think we'll also try to monitor any questions in the chat in the YouTube as well. I don't see any questions quite yet, but I have a quick question for you. You mentioned that one of the big improvements with this computer was moving from using bosons to fermions to reduce the noise. So is that still strontium or cesium, or is there something else? Or?
It's strontium. Strontium, depending on the number of neutrons that we have. So strontium 87 is a fermionic atom. So yes, we are always using now fermionic strontium for building the best clock in the world. So we can also use strontium 88 that has one additional neutron. But for example, these are bosons, and some new experiments that using what is called optical tweezers are starting to build clocks with them, because in principle, if you have a tweezer, so you can hold only one atom per side and have no collisions. So for that, because collisions is not important, the statistics also not that relevant. But for the state of their atomic clock, yes, all of them are operating with fermions, strontium 87.
Okay. We have a question about what's the fundamental theoretical limit on the precision achievable with an atomic clock? Is it the Heisenberg uncertainty principle, or?
Well, actually, there are. I mean, the fundamental. I mean, the fundamental. At the moment, the fundamental level is perhaps to control what is the vibration of the mirrors that allowing us to stabilize the laser. Because I mean, the problem is that what we are using to actually read the frequency of the atoms. I mean, the atoms have of course, the atoms have a quantum uncertainty principle, but the point is that we can average for very, very long time, and the more average time that we can reduce our signal to noise. But at some point, and now, the fundamental limitation that we have is the noise of the laser, and the lasers are stabilized by an optical cavities, and the optical cavities have some vibration. So one of the biggest challenges that Jun's group is trying to overcome is is trying to build the best cavities that are not sensitive to the thermal noise of the mirrors. So otherwise, in principle, yes, there is the uncertainty principle. But however, if you pack more atoms and you wait more time, you can always average out as much as you can. So our goal is to see, for example, of the effects of quantum gravity and even gravitational waves and all of this, we will need to go to improve at least 2 or 3 order of magnitude better than what we can do today.
Okay. All right, any other questions? And you can type them in the chat or the Q&A. All right, I see another question. You mentioned GPS satellites each have 4 or more atomic clocks. How large must the clocks be in terms of their dimensions in mass, to fit?
Oh no, well, the atomic clocks that are miniaturized atomic clocks, they are really small, and that's why they can fit in the satellite. So they are using small chips to put the clocks in that. I mean, it's like an excellent question because, of course, current optical lattice clocks that are in June's lab, they are huge. They occupy a table, an optical table, and they cannot fit in a satellite. But there are technologies that actually are making these clocks very tiny, and they have been they're in satellites, there have been even in rockets. These are just very small objects that are that I mean they're made at a micro scale size.
See, all right, another question. Is the definition of the meter set by the cesium transition plus the speed of light?
Yes, exactly. That's a very good point. So exactly. So the frequency of the second, the frequency, the measurement of time sets very other different standards. And yes, they you know the frequency of the velocity of the light, then on the second you can define the meter. Exactly.
And then one more question I see about time standards. I guess a couple of years ago there was a presentation about the NIST atomic clock, and for example, like leap milliseconds are sometimes added, and this gave introduced discrepancy with GPS satellite clocks. And so I guess they're wondering if I don't know. I'm not sure if you would know, but is do you have any idea what's been happening with changing time standards, or whether or not?
Yes, at the moment, the standard remains to be cesium. I mean, not the strontium. The problem is that if you have to have enough clocks operating with the strontium in order to set a standard. So currently, there are not too many laboratories that can be used to that operate that are active to actually change the definition of the second using another type of atom. But hopefully, it's not that far away in the future that we are going to have the second defined in terms of an optical transition like strontium and also ytterbium. There are the two candidates for actually defining the second at the moment.
Okay, I think those are the only questions I see at the moment. So, all right, well, oh, sorry, one more. Just, yeah, I guess someone is asking about, since bosons can all occupy the same quantum state, isn't that desirable? Because then you don't have this energy level split due to interactions of the individual bosons.
No, unfortunately, that's not the problem. I mean, the levels that I was showing are the internal levels of the atom. But what happens is that when if bosons want all to be, for example, in the law in the same internal state, so depending, therefore, there is an I mean, there is an interaction energy when they're all together because they're colliding and bumping into each other. So they can, and because two bosonic atoms that are in the same internal state can collide, and when they collide there is a change in energy, and this is the energy that we don't want, this internal energy associated with actually the collisions of the atoms. So that's why they are not desirable. Fermions, on the other hand, they have to be in different internal levels. So I didn't mention in detail, but for example, the internal level that we have is momentum. Atoms with the fermion, when we have fermions, they two identical fermions, if they live, they are trapped in our experiment, they have to have different momentum. And when they have different momentum, the way that they it costs a lot of energy for them to be able to collide. And that is why the collisions are suppressed. So I don't, I mean, it's a little bit, so bosons want to be all together, and when they are all together, they tend to collide to each other, and these collisions generate a shift in the transition frequencies that depends on the density of the atoms. So if I have certain number of atoms, then I have some frequency splitting. If I have another number of atoms, I have another energy splitting. And because in the colloq they cannot always control that they each time that they measure they have the same atom number of atoms, then they are going to have fluctuations in the frequency that is correlated with the atom number, and this is not good.
Great. One last question. I think you alluded to this a little bit earlier. The question is, why are strontium atoms, why do they behave as fermions given that their atomic number is 38?
It's 87, and it's 87, and it's depending. This is depends on the number of protons and neutrons that the atom has. For example, strontium 87 is such that the internal spin of the atom is the total spin of the atoms is a half integer number, and therefore you have a fermion. If you add another neutron and you have another neutron, then you are making the internal quantum spin actually an integer number, and that's why strontium 87 is a fermion and strontium 88 is a boson. So yes, so it just depends on the number of neutrons that you have in your system, and yeah.
Okay. Right. I think those are all the questions I see. So again, thanks again for this fantastic talk and taking some time out of your Saturday. And thanks to all of you who have attended and taking time out of your busy Saturdays to hear about this really exciting research. And again, this wraps up our talks for this academic year. And I hope we'll be back next year and can see some of you in person on the CU campus. And all right.